Hi everyone, today we'll look at the paper MiniCPM, Unveiling the Potential of Small Language Models with Scalable Training Strategies. So this paper basically introduces two different models which are pre-trained, one with 1.2 billion parameters and the other with 2.4 billion parameters. And they basically describe a bunch of different training strategies which make these small language models more efficient and achieve a performance comparable with larger models with 7 and 13 billion parameters. So among the training strategies, they also introduce a learning rate scheduler, which they say is better than a cosine learning rate scheduler, which is mostly used by folks. And they also say that there's a higher compute optimal data to model ratio than what was previously established. And they also perform hyperparameter optimization using a bunch of different wind tunnel experiments at a smaller scale and scale that onto a bigger scale model effectively. There are different family of models such as DPO, basically, which is the direct preference optimization model, the mixture of experts model, and the long context model. So to begin with, let's look at the wind tunnel experiments. So essentially, they do all their experiments in a very small scale model, and then they see how they can transfer the hyperparameters onto a larger scale model. They use the MUP hyperparameter search. So for more details, folks can basically read these paper, the tensor programs paper, and basically what they do is they fine tune a model at a smaller scale and then perform almost like a zero shot transfer to a bigger scale without directly tuning the hyperparameters of a bigger model at all. And this mute transfer is illustrated in the paper. They basically show empirically and mathematically that this does work, and you basically find the hyperparameters for the small model, and then you would multiply it based on whether it's the input weights or the learning rate. You would multiply it by what's given here, by the fan in or the fan out or the depth of the bigger model. Depth would be the number of layers, fan in would be the number of neurons connecting to a particular neuron from the previous layer, fan out would be the number of neurons a particular output is connected to. More details can be found in the paper, but they use this kind of a hyperparameter search, and then they find that they are able to use hyperparameters from a smaller model. They validate this with the learning rate, and they find that the base learning rate of 10 power minus 2 can, in fact, transfer across these different model sizes. The next thing they do is to actually compute the optimal batch size, and they use the C4 dataset for the batch size and loss computation. So they experiment with different model sizes as shown here, and different batch sizes and different number of tokens. So for a particular batch size and different tokens, you can see like one vertical line here. This would be one training run, and then they connect all those points which have similar loss, and they get these parabolic curves. They basically take the lowest value of the parabolic curve as the optimal batch size, and they plot the batch size versus loss, and they find that there is a log-log relationship between both these. So this basically means that to start off, you wouldn't know what the batch size is because you need to have some runs to get a good estimate of the loss. So they start off with some initial batch size, and then they compute the loss and then readjust the batch size dynamically after each checkpoint. So that's how they find their optimal batch size. The next thing is the learning rate scheduler. This is the warm-up stable decay learning rate scheduler. So typically people use a cosine learning rate scheduler, which can be seen here. So if T is the number of steps after which the learning rate scheduler reaches 0, it's been found that it's ideal to have T equal to S, where S is the total number of tokens you have. So basically, you kind of lower the learning rate according to the number of tokens you have. So here they propose a new learning rate scheduler, which is the WST learning rate scheduler, and they say that's better than the cosine scheduler. So this consists of 3 stages: the warm-up stage for W number of steps, and then a stable state where the learning rate is kept constant until T steps, and then there is also an exponential decay stage, which is a function of S minus T, right? And then they find that during the decay stage, the loss basically decreases dramatically, as can be seen here. And they find that 10% of steps are enough in the decay stage. So with this kind of a scheduler, the advantage is you can basically have multiple stable stages. You can do this continued pre-training, sort of pick up a checkpoint from a stable state, and then just make sure that the learning rate is whatever is the learning rate at the stable state, meter, and then continue with it, and just have one decay stage at the end. They then fit a curve for the compute and the loss, and they find that it observes a power law relationship that's shown here. So that's figure 6 here, and they basically have one curve. The red curve is for a bigger model, which has 0.17 billion parameters, and then you have the other curves for a smaller model, which has 36 million parameters. And then you look at the final losses. So they're trying to fit a curve to predict the final losses, and they find that there is a power law relationship between the loss and the compute. And they also find that the bigger model basically reaches 3.32 loss here, as can be seen in the figure. And they find that their optimal loss envelope, which they predict using the equation which they get after fitting the curve, also reaches 3.32, but after 4 times the compute. As you increase 4 times the compute, you basically get the same value of the loss compared to the bigger model. And they also look at the decay stage. They look at the weights, the first and second order derivatives, the curvature of the loss, and they basically say that in the decay phase, the gradient norm is less. So you can see that in figure 8 here. So if you look at the gradient norm, you plot the gradient norm, the decay phase is basically towards the end. And you see that the gradient norm basically decreases at this stage. And they also look at the cosine between the gradients, and they find that that's mostly positive here. So the updates are more consistent and aligned. And they look at the first order and the second order derivatives, and they also look at the curvature. So the curvature basically increases slightly in the decay phase, indicating that it's proximal to a local optimum. The next thing they do is basically recompute the scaling laws with their new learning rate scheduler. So if you're using a cosine learning rate scheduler and you want to compute the scaling loss, you basically would have to compute the loss of m different models and m different data sizes, right? And this would take m squared c compute time, right? So if c is the compute time required to train one model. Now, because of these multiple stable stages, you can basically have just one training iteration and save multiple checkpoints and apply the decay stage to each checkpoint differently to get the model trained on different number of tokens, right? So you don't have to start off from scratch as in with the cosine scheduler. So that's one of the advantages of using the WST learning rate scheduler. And then they fit the equation, the scaling law equation, the power law equation, and they find the alpha and beta coefficients is 0.29 and 0.23. And they emphasize that we need to focus more on the data scaling than the model scaling. And they also find that the ratio of the optimal number of tokens to the optimal model size is much greater than what was reported in Hoffman et al. So basically, the gist of this slide is that smaller models can absorb more data than what was previously thought based on Hoffman et al. Paper. So the next thing they do is basically they introduce a different pre-training strategy. So typically we do the pre-training with a large pre-training data set. So now they're saying that including some supervised fine-tuning, high-quality data along with the pre-training data is actually better than just using the pre-training data. So you have the pre-training phase, and this corresponds to the warm-up and the stable learning rate for the WST scheduler. And then in the decay phase, where the loss is more and you don't really need a very high learning rate, you use the SFT data, around 20 billion tokens. And then again, you do a supervised fine tuning after you do the pre-training and decay phase of around 6 billion tokens. And you're basically continuing the learning rate from the first decay phase. So the models, both the models, the 2.4B and the 1.2, are trained in this way. And the vocab size which they use for these models are 122,000, around 123,000 tokens and 73,000 tokens. And they also have other details such as they share the embedding layer of the input and the output and different layers for the 2.4B and 1.2B model. They use group query attention for the 1.2B model. And they evaluate these models on different benchmarks. Table 3 shows the results of that. And what they find is these small models, which are 1.2 billion, are perform better than models which are 7 times its size, right? And they also see that Phi2 is something which performs better than their models on a bunch of different benchmarks like BBH, ARC-EZ, Challenge, and Hella Swag. And then they have different flavors of their models. The first one being the direct preference optimization model. And then they compare this along with other chat models, which have way more parameters. And they find that the performance is comparable, but not as good as their pre-training strategy models, right? And then they also have, and their DPO, they perform on the ultra feedback alignment dataset, and they also have a proprietary preference dataset. They use a cosine learning rate scheduler to do this. They also increase the context length from 4K to 8K. And they also use the WST scheduler when they're training this long context model. And for extension of long context, they apply the adjusted base frequency, which can be found in the paper. And then they also employ the NTK aware rope scaling and curriculum learning. And the evaluation results are shown here, where the model actually performs better compared to some of the bigger models. And then they also have a mixture of experts model, and then they see that the mixture of experts model indeed does perform better than Llama and Mistral in some of the data sets. So to conclude, this paper basically introduces different training strategies, a learning rate scheduler to basically make the pre-training of smaller models more efficient, and so that they can compare with bigger models which are like 7 times their size.